Okay, so the city of Lightsville has 136 streetlights, and as part of an urban renewal program, and again, your numbers might be slightly different than the numbers I have here, but the method should be the same. So as part of an urban renewal program, the city council has decided to install, can you move a little bit? Thanks, and have operational 3 additional streetlights at the end of each week for the next 52 weeks. Each streetlight costs $4 to operate for 1 week. How many streetlights will the city have at the end of 36 weeks? So again, some people like to write formulas before they answer questions like that. Some people like to answer that question and that will inform how to write the formula. So whichever kind of person you are, it's fine. So like A and B, it might make more sense. It might feel more natural for you to answer question B first. Okay, so let's see. We have 136 streetlights already, and we're going to add some to that, right? We are going to add 3 per week for 36 weeks. So 3 times 36. And that should be how many we have after 36 weeks. We already have 136, and we're adding 3 per week for 36 weeks. So 36 times 3 plus 136 is 244. I want this to go away. Whatever. Okay. What was it? 244, right? Okay. And then B, how many streetlights will the city have after N weeks? Well, it will have 136 plus 3 per week for N weeks. So that would be our explicit formula. And then C, what is the cost of operating the original 136 lights? So you would say, oh, 136 times $4 per week times 52 weeks. Because those 136 already exist, you have to pay to operate them for all 52 weeks. And 136 times 4 times 52 is $28,288. All right, and then D, which is the really hard part. What is the additional cost for operating the newly installed lights for the 52-week period? All right, so remember, they're adding 3 streetlights at the end of each week. So at the end of week 1, they've added how many? 36 new streetlights, right? Oh yeah, 3 per week. Okay. So at the end of week 1, they've added 3 new streetlights, and it costs $4 per week to operate each one. And how many weeks do we have to pay for that operation? 51, because we added it at the end of the first week, so that whole first week we didn't have to pay to operate those. 51 weeks. Okay, and then the next week we're going to add 3 more streetlights. They're going to cost $3 a week, $4 a week for each of the 3 lights. And how long do we have to pay to operate those? 50 weeks, because they didn't exist for the first 2 weeks. Yes, please. And then we do that again, 3 times 4 times 49. Right, and then the last number in this list of numbers that I'm adding up is going to be 3 streetlights, $4 per week. How many weeks? 1. Right, so we just keep doing that until we have just 1. All right, so this is a list of numbers, long list of numbers. I don't want to write it all out because how many terms are in that list of numbers? 51. 51, good. So instead of writing them all out, I'm going to do my little trick where you add the first term and the last term, multiply the result by the number of terms, which you just told me was 51, and divide by 2. So my sum is going to equal the first term plus the last term. So my first term is 3 times 4 times 51. The last term is 3 times 4 times 1. First term plus the last term times the number of terms, which is 51, divided by 2. All right, so we'll pull up my calculator. So 3 times 4 times 51 is 612. 3 times 4 times 1 is 12. Okay, 612 plus 12 times 51 divided by 2 is $15,912. Two. Yeah. There are no Z's in the problem. Does that make sense? Is that clearer? Sure. Okay, let's move on to talking about exponential population growth. Remember, Project 2 is due today by midnight. So last class, we learned about linear growth models. And a linear growth model is where you add the same amount at each transition. And remember, linear growth results in an arithmetic sequence. In an exponential growth model, you multiply by the same amount at each transition. And exponential growth results in a geometric sequence. So here's an example of exponential growth. The Earth's population was about 6 billion in the year 2000. Assuming the population doubles every 45 years, see if you can project the population in the year 2045, 2090, 2450, and 2900. Okay, so let's talk about this first part. In the year 2000, they told us the population was 6 billion. So rather than writing a 6 with 9 zeros after it, I'm just going to put billion to say billions. Okay, so the population doubles every 45 years. So what's the population in 2045? 12 billion, right? 45 years have passed, so the population doubles. And then that number doubles because 2090, another 45 years have passed, so this will be 24 billion. All right, and then 2450, a lot more than 45 years has passed, right? So how did you come up with the population for 2450? Okay, hold on, slow down. So you said you wanted to know how many years had passed from 2090 to 2450. So to know how many have passed, you subtract 2450 minus 2090, and you said, oh, that's 360 years have gone by, right? And then to know how many times you should double the population, you have to know how many sets of 45 years that is. So you divide by 45, and you said, oh, 8 sets of 45 years have gone by. That means you double 8 times. So 2450, I would say, I would take my 24 billion and multiply by 2 8 times. That's the same as multiplying by 2 to the 8th. Yep. Because multiplying a number by itself is the same as an exponent. The notation we use for that is an exponent. So if I do 2 to the 8th, need a better calculator here. 2 raised to the 8th is 256 times 24 billion is 6,144. Still in billions, which you could also write as 6.144 trillion. Okay. Yeah. How else, did anybody do something different than what we just described there? Anybody come up with that 6,144 in a slightly different way? Yeah, Jasmine? Okay, so instead of saying how many years have passed from 2090 to 2450, you started with the 2000. That's perfectly acceptable, okay? So instead, I could say, oh, from 2000 to 2450, 450 years have passed, which is 10 sets of 45. So if you start at the 6 billion, you have to double 10 times. Okay. So I could also write this as 6 billion, my original starting amount, and double it 10 times, instead of starting at the 24 and doubling 8 times. A general formula. We'll do that in a minute. Okay, so for yeah, so the way that you described to me, you said, well, how many years have passed from here to here, right? And you said 360, and that's 8 sets of 45. So if I start with 24, I have to double it 8 times. Okay, so Jasmine said, how many years have passed from 2000 to 2450? 450 years, which is 10 sets of 45. So if you start with 6 billion, you would double 10 times. That makes sense? Because the first 2 times gets you to the 24 where you started. Okay, so you can do it either way. And then for 2900, I would say, oh, okay, well, I could start with 6 billion. And how many times do I have to double? 20. Because 900 years is 20 sets of 45. To the 20th. So 2 to the 20th times 6 billion is 6,000,000. Okay, so that's 6,291,456 billion. So if I try to translate that, I would get 6,291,456,000,000,000. Why not?
I'll never figure out what you get past.
No, I'm not gonna try to mess you up with place value. No. So, but this number is 6.29 quadrillion. You just say 6.29 quadrillion. Clearly, the Earth cannot sustain this kind of growth, right? Okay. But the Earth has been growing at this rate, so we can use this rule to try to go backwards in time, right? So how would you figure out the Earth's population in 1955? Divide by 2, yeah. But how many times should I divide by 2? Once, yeah. Because 45 years before the year 2000 was the year 1955. It's 45 years earlier, right? 2000 minus 1955 is 45 years, right? So to go backwards in time, 45 years, we should divide by 2. Okay, so make another little table here, 1955, we should have 3 billion. And then 1820, how many people would there have been? How many years ago was 1820 from the year 2000? 180? Yeah, 180. How many sets of 45 is that? 4? Yeah, it's 4. So I would have to divide by 6 4 times. Divide 6 by 2 4 times. So I could just do it out. I could just do 6 divided by 2, divided by 2, divided by 2, divided by 2, and I would get 0.375 billion. Or 375 million. Yeah, question.
This is exponential growth equation for population.
Uh-huh.
I know in biology or something in high school, we learned the actual equation, like something like 100 or whatever. equals whatever.
Mm-hmm. Yeah. Populations generally they cannot maintain this rate of growth because there are only so many resources, there's only so much space. So a population like the Earth's population of people might look like it's growing exponentially for a while, but it can't maintain that, and it actually grows according to something called the logistic growth model. And we'll talk about it at the end of this class. Yeah, thank you.
So the last one you divided by 4.
I divided by 2 4 times.
By 2.
Yeah. Sure. Yep. So I started with 6 billion, right? And I divided by 2 to the 4 times, so 2 to the 4th. Yep. Divided by 2 to the 4th. Or, no, it's not, no roots, it's 2 to the 4th. Dividing by 2, yeah, I'm going backwards, which means divide.
Yeah.
Right. Or you could multiply by 2 to the negative 4. If anyone has seen negative exponents, it's 2 to the negative 4 is the same. Multiplying by 2 to the negative 4 is the same as dividing by 2 to the positive 4. You can do either one, whichever one feels natural to you. All right, and then last one, the year 1100. How many years before 2000 is the year 1100? 900 years, which is how many sets of 45? 20. So I have to take my 6 billion and divide it by 2 20 times. So I'm going to divide by 2 to the 20th. So first I'm going to raise 2 to the 20th in my calculator. And then I'm just going to store this number for a second. And then I'm going to do 6 divided by that number. And it's a small number, 0.000057. 2, 3, 4, 5, 5, 7. 20th. Yeah. That is 57,000. Yep. So right now this is billions, right? So if I move the decimal 3 to the right, it'll be millions. And then move it another 3 to the right and it'll be thousands. So, oh, actually it's 5.7 thousand. That seems crazy, right? There have to have been more people than that. Yeah, move the decimal 3 to the right and you get millions. 3 to the right and you get thousands. 5,700 people. So this is a poor model, right? Exponential growth only can model small pieces of time because populations, again, don't really follow exponential growth. All right, so here's a problem for you to think about. Can you figure out the Earth's population in the year 2120? See if you can figure out and explain why this is harder than the previous ones. Okay, so most of you have started to approach this problem the same way we did the other ones, right? You said, oh, 120 years have passed, right? So I'm going to do 2,120 minus 2,000. 120 years have passed, right? And then you say, okay, how many sets of 45 is that? Because however many sets of 45 it is, that's how many times you double the population. So you divide by 45 and you get, oh, this is what makes it a trickier problem than the previous ones, right? Because it's not a multiple of 45. 120 is not a multiple of 45. However, we can still solve the problem the exact same way we did the other problems. Start with 6 billion, and we're going to double it 2.67 times. So we raise it to the 2.67. So even though we haven't defined what it means to raise something to a decimal, because like 2 squared we know means 2 times 2, and 2 cubed means 2 times 2 times 2. 2.2 to the 2.67 we haven't really defined, but if we follow this same thing that we did in the previous ones, let's see what we get. So let's You can plug it into any calculator. What do you mean?
Like that formula, I don't understand. The 6.
You can plug it into any calculator that knows the order of operations can do that.
And then put this on your answer.
Yeah, so if I do 6 times 2 raised to the 2.67. So I can just type it all in because this calculator knows the order of operations. And most calculators do. All right. Yeah, Emma?
So I did what you're talking about, and I basically took a third of 24, see,
Mm-hmm.
plus, or times 2 is 16, and I just add that on top of 4, get 3.
Mm-hmm. So it's close. It's close. Let me just go over the calculator stuff for a second, and then I'll answer that question. Okay, so to type in 6 times 2 to the 2.67, you hit 6 times 2, and then hit x to the y or y to the x or the caret, whichever you have, and then type 2.67 and hit enter or equals. Okay, so Emma's question, she said 2.67 is somewhere between 2 and 3, right? So we're doubling somewhere between 2 times and 3 times. So if you double twice, you do 6 billion times 2 squared, and you get 24 billion, right? And if you were to double 3 times, you would multiply by 2 cubed, and that would be 48 billion. And it would make sense that the answer, right, for 120 years would be somewhere between doubling twice and doubling 3 times. Doubling twice is 90 years, and doubling 3 times is 135 years. Right? So 120 years is somewhere between 90 and 135. So the answer should come out between 24 billion and 48 billion. The answer we have here is between there, so that feels good, right? And then Emma said 0.67 is 2/3 of the distance between 24 and 48. So if you go 2/3 of the distance between 24 and 48, you end up at about 40, right? At exactly 40. Yep. Yep. So if you say, well, 24 to 48 is 24 years, 24 billion, right? And if you break 24 into thirds, those are 8-year chunks.
45 into thirds, 15.
Yes, yes, yes. Okay.
45.
Uh-huh.
Find a third.
Okay, so those are years though, right?
Yes.
So
Because that 45 I took because that's the amount of time the population doubles.
yep.
The 30 is the remainder. So I took fraction of the time in between, the doubling time, which was 24, and I split it into thirds.
Mm-hmm.
Double it into 2/3, 45.
Okay, so you took so tell me exactly what you did to get the 40.
Okay. So you have the 24 billion.
Yep.
48 billion.
Yeah.
In between that is 24 billion.
Yes.
Like I said before, 15 goes into 45 3 times.
Yeah.
Goes into 30 twice.
Yeah.
So you need 2/3 of that doubling time period.
Yep.
Which is the 24 billion population.
Yes.
Because you're between that 2 and 3.
Right.
So find a third of 24.
Right, which is 8, right?
And then you multiply it
By 2 to get 2/3, which is 16. 24 plus 16 is 40. Yeah. Good. Okay, so that makes a lot of sense, and it's really good problem solving. The answer is going to be a little bit off. Because so when you're adding, if you're adding, you're saying, okay, so 1/3 of the way between here is 8, 2/3 is 16. If you add 16, when you're adding, that's actually linear growth and not exponential growth. Over a short period of time, linear can approximate exponential, which is why you got close, right, and came out as 40. But instead of adding a third, right, there should be some number that you can multiply by instead of finding what to add. Okay, so that is a nice approach, and it will get you really close to the answer because you're only using linear over a small time interval, but it's not going to be exact. So rather than adding the 16, really you should be multiplying by 2 to a smaller power. All right, so here's a new example. A rabbit population starts at 1,000 and increases by 20% each year. Let's find out how many rabbits there are after 1 year, 2 years, 3 years, and n years. So we'll have n for years, r sub n for rabbits, and April, yes, I randomly picked capital R to represent my population because it's rabbits. Yeah. You could pick any number you want. You could call it P for population, pick any letter. Okay, so in year 0, right? In year 0, we have 1,000 rabbits. That's the current year, right now. 1 year later, we're going to increase this population by 20%. So how many rabbits am I going to have? 1,200. That's great. I'm going to add 200 rabbits. Right, so the way you figure that out, how to increase something by 20%, yeah, take 20% of it and add it to it. So I would have 1,000 plus 20% of 1,000, which is 1,200. A quick shortcut for increasing a number by 20%, instead of having to do 2 steps where you multiply by 20% and then add it to the original, you could just start with your 1,000 and multiply it by 1.2. Right? The 1 means keep 100% of what you have, and the 0.2 means add an additional 20%. Okay, so 1,000 times 1.2 also gives you the 1,200. All right, the next year, I want to increase by 20% again. So now I have 1,200 rabbits. So I'm going to do 20% of 1,200. I'm going to keep all of the rabbits that I had the year before, 1,200, and add 20% of 1,200. Or I could just multiply 1,200 by 1.2, right? Keep 100% of your rabbits and increase it by 20%. And that, I think, gives me 1,440. Either way you calculate it, you have 1,440 rabbits. All right, let's look at year 3. In year 3, I'm going to take my 1,440 and I'm going to multiply it by 1.2. That increases it by 20%. And I can't remember the answer to that one. 1,728. Oops. 1,728 rabbits in year 3. Okay, so if I wanted to write a formula, right? Let's write a recursive formula. Okay, so how am I determining the number of rabbits in any given year, knowing how many I had the year before? R sub n minus 1, that's how many I had the year before. And then what do I do to that? Times 1.2. That will increase by 20, that will give me a 20% increase. Take however many you had the year before and multiply by 1.2. And whenever you do a recursive, you should also give the starting amount, because you can't implement a recursive formula unless you have some number to start with. So we write down r sub 0 as 1,000. All right, let's look at the explicit. Okay, so for explicit, think about what we're doing, right? So we're starting with 1,000 rabbits, and every year we multiply by 1.2. Right? Multiplying by 1.2 over and over and over again, what notation do you use to represent multiplying by a number over a power? Right? So I'm going to start with 1,000. I'm going to start with 1,000, and then multiplying by 1.2 over and over and over again. So I would raise it to the n. That is the explicit formula for the number of rabbits in year n. For the population problem? Good question. So for the world population problem, I would say if I want an explicit formula, I would let the year 2000 represent year 0, right? That's where we're going to start measuring from. So I would say my world population in year n is going to be 6 billion, right? Times 2, and I'm going to multiply by 2 over and over and over again. So I would raise it to the n. But in this particular problem, what does n represent?
45 years.
Sets of 45 years. So you would have to write down n is the number of sets of 45 years since 2000. In exponential growth, you will always have an exponent in the explicit formula. So the number 1.2 in the rabbit problem is called the common ratio. In the world population problem, that common ratio would have been 2, because you multiply by 2 all the time. Right? It is the ratio of the current population to the previous year's population. So here are the general rules, general formulas for exponential growth. Again, you don't need to memorize these because you can come up with these formulas by sort of reasoning it out, but they are here. You can write them on your cheat sheet, bring it to the test. If you want to write a recursive formula for an exponential growth model, you have to give the starting amount, P0, and then P sub n, the population in year n, would be P sub n minus 1, which represents the population from the year before, times whatever the common ratio is. Right? In the rabbit problem, it was 1.2. And an explicit formula, P sub n, the general population in year n, is equal to your starting amount. For us, it was 1,000, or the 6 billion, times your common ratio raised to the n.
So when we're on the test, we plug in our numbers.
Yep. Okay, so here's another problem for you to consider. A bank account can be thought of as a population of money, right? Dollars living in a bank account. Which would you rather have? $1 million today, or a bank account that begins with 1 penny and doubles in value each day for 30 days? Okay, so what have you decided on? Should I give you $1 million today or 1 penny today? The penny, and double it for 30 days. The penny is a far better deal, right? Yeah, you have to have a little more patience, but if you can wait the 30 days, you end up with how much money? 10 million something dollars. Yeah. 107. Ooh, let's figure it out. So we've got 10 million, we've got 107 million, and we've got a 56 million. So let's see. So 1 million, yeah, all of you agree that it's more than 1 million, yeah. All right, so otherwise, I'm going to take 1 cent, right? 1 cent, and I'm going to double it every day for 30 days. So I'm going to multiply by 2 to the 30th, because multiplying by 2 30 times is 2 to the 30th. And that comes out to, get my calculator, 1 times 2 to the 30th, 107,374,1824. That is cents, right? Because I started with 1 cent and I doubled it. So my units are still cents here. So how do I get dollars from cents? Divide by 100. So take this number. If you divide it by 100, it's just going to move the decimal 2 to the left. So I have 107,374,18.24. 0.24. $10,737,418.24. So I choose option 2. If you start with 0.01, then you're already in dollars, right? So you would say, oh, $0.01 times 2 to the 30th will give you that same number. Okay, so like Emma mentioned earlier, exponential growth is generally not sustainable because resources like food and water and space are always finite. So population can't just continue to double, right? That's impossible. It could do that for maybe a long period of time, but eventually it will level off, right? The population growth will slow and level off at something called the carrying capacity of the environment. And this type of growth, right, at the beginning, it's growing very fast, and that looks exponential, right? The beginning is a little bit slow, and then it hits this really fast part right about there, where it's increasing really quickly. That's where the Earth's population seems to be right now. We're in this like really fast growth period. And then eventually, it would be predicted that the growth will slow and level off at some maximum carrying capacity of the environment. There are formulas for logistic growth. We're not going to learn them. They're in your textbook if you're interested. I'm not going to test you on logistic growth. I just thought you might find this interesting. Yeah.
So this might be a little morbid, but is there a way to test like death rates because of the carrying capacity of the environment?
To tell like whether we are.
People are going to die in 30 years. Hold them because we can't support them in their lifestyle.
Yeah, there's a whole branch of science that deals with population size and population growth.
Well, that's what I'm thinking because like I'm thinking kind of like Nostradamus a little bit right now.
Yeah.
Did all that.
Yeah. Mathematicians and scientists talk about this all the time. There's no way to know absolutely for sure what the Earth's carrying capacity is, but there are lots of predictions and yeah. Yep. You can predict it, you might not be right, but there are lots of models that we use to try to predict it. Yeah. A lot of people right now think that the Earth's population is like right in this spot where you switch from really, really fast growth to slightly slower growth, right? So this is science's current prediction of where we are. They think population growth is about to start slowing and approaching a carrying capacity. Oh, so yeah, another way that logistic growth can look, right? We've got this carrying capacity. It's possible, instead of just leveling off at it, that it could go above it, and then it has to come back down like that, right?
Well, that's what I'm kind of saying. I'm thinking like apocalypse term, like how to study, I guess, that.
Yeah. So once it goes over the carrying capacity, something in nature will bring it back down.
Yeah.
Whether it's not enough food and people can't survive, or some kind of natural disaster, yeah. Something will have to bring it back down if we go above the carrying capacity. Yeah.
Go back a little bit, just right on for this problem. Yes.
The money problem?
Yeah.
Yep. So my explicit formula, I would do 1 cent times 2 to the n. That would be my money in year n.
Wait, what happened?
Yeah, well, equal signs are commutative, right? You can write them in. So my money in year sub n would be 1 cent and double it n times.
Can you do the 2.0 thing again? Or 0.01 thing again? Or no?
Yep, because this one, your units is in cents. You could also write this as 0.01 times 2 to the n, and your answer will come out in dollars. Either of those would be fine. You just have to know which units you're working with, right, to be able to answer the questions. M sub n minus 1 times 2. Yeah, so I'll write recursive for this problem will be m sub n is equal to m sub n minus 1 times 2. Does that agree with you? Do you have those? Okay, so we have an activity. Bacteria are scary, and we probably will not have time to go on, so you can spend the last 10 minutes or so working on the bacteria are scary problem.